Okay, we are back to the ring of current, and we are back to the point we'd really like to draw a magnetic field through this point and figure out what the direction would be. And we took our detour with the cross product, and what we came out of with that cross product quick detour is that the result of a cross product, in particular a dx cross an r, where dx is the direction of the current at that moment, is perpendicular. The result is perpendicular to both dx and r hat. So if you look up here at this figure here, you go, what vector could I possibly draw here that's perpendicular to both r hat and dx? That's going to be the direction of your magnetic field, or your little differential magnetic field. But the vector you draw has to be perpendicular to both of these vectors, both of them. So if I sort of take these two purple vectors and maybe lift them out of the surrounding figure just for a moment here, it might look something like this. This is the dx right here. That's the direction of the current at the top of the loop, and here's the r hat, the vector that takes me down to my observation point. What vector would you draw that's perpendicular to both of them? Or if you were going to use the right-hand rule on this, if you put your fingertips in the direction of dx and curl that into the direction of r hat, you'll see the vector will point straight up like that. And maybe it's a bit unfair because it's a plane of the page, and agree that the resultant vector would be straight out of the page like this, but we're not quite in the plane of the page right here. We sort of have this dx vector which is pointing out this way. You know, if I get my little model loop back that looks something like this, this dx vector sort of pointing over this way, and this r hat vector sort of pointing down like that. So where would that ultimate direction be? Well, perpendicular to both. The only vector I can draw here that's perpendicular to both of these vectors is actually this one right here. That's going to be the direction of my dB. It's perpendicular to r hat right there. And if I would sort of imagine taking this vector and translating it all the way up to the top like that, up here like that, this vector would also be perpendicular to x hat right there. So kind of a brain twister in there, and please review your book if you have any question on that or ask me questions, but there's going to be my resultant magnetic field. So when we have that going now, we're sort of free to proceed and sort of attack the problem a bit more. And again, in your mind, if you would contrast this once again to the direction of the electric field, which was down like that. Remember, we had a DE like that, just very different problem. DE points down along that r hat direction, but dB does not because of that cross product in there. It throws everything at a 90 degree angle like that. So we can proceed a bit. Things will be pretty normal now insofar as the derivation goes. This dB, wherever direction it's pointing at, makes an angle alpha with respect to the z-axis. And once I have that angle alpha like that, I'm free to write a dB, I guess we'll call that y here, and down here there'll be a dBz. There are going to be two components, and I can find those two components using my trig functions. I think in this case here, you'd probably agree that dBz is going to be equal to dB times the, cosine of alpha. And dBy here is going to be dB times the sine of alpha, something like that. And you can see there's going to be a bit of symmetry in this problem here, that for any little segment of current that goes around the ring like this, the dBy is always going to cancel, as will any dBx that would come into or out of the piece of paper like that. So we're not going to worry about the dBy, because these are just going to integrate out to be zero as we go all the way around. But there is nothing to cancel the dBz. So we have a bit of a clue about the direction of the magnetic field due to a ring like this. It's going to be a dBz, sort of all in the z direction like that. So we can sort of continue the derivation a bit. Here's our dB here, and we just immediately need to go to dBz here, our only surviving component, mu naught over 4 pi I dx over r squared. And I hope you see here that dBz is going to involve the cosine of alpha, and the cosine of alpha you just put right here, and so that would sort of do your vector projection bit for you. Now, sort of the rough part about the problem then is like, well, what is alpha? You know, how are you going to find this alpha? Well, you got to look very carefully at the figure here, and you see this is alpha right here, and this is the 90-degree angle that's formed as a result of the cross product. The dB is perpendicular to r hat, and there'll be another angle in here. We can go ahead and call that, I don't know, I guess theta if you want. We sort of use theta a little too much, but we'll just use it again in here. And the reason why we need theta is because theta is related to the geometry of the problem. In particular, if our observation point is distance z from the hoop, that'll be related to theta, and if the hoop here has a radius r, that'll be a radius r like that. So you can see that maybe you can write something like this angle here might be related to this one, and the way you can get that is if you look at these three angles here, you can sort of see that theta plus 90 degrees plus alpha is equal to 180 degrees. Where am I getting all this from? because this is a straight line right here, 180 degrees, and these three angles sort of eat up that space in there. So you can see if you sort of work on this thing that alpha comes out to be 90 minus theta, and so the cosine of alpha then just comes out to be the sine of theta. Where am I getting that from? Because the cosine of alpha is going to be the cosine of 90 minus theta, and there's a trig function that says the cosine of 90 minus theta is the sine of theta. So see, I can sort of work down and get my b dz to be mu naught over 4 pi I dx over r squared times the sine of theta. And this video is getting a little long and boring, I suppose, so I'm just going to wrap this up and say, look what you do now. The sine of theta can now be related to this angle over here. In particular, the sine of theta is going to be the opposite side. It's going to be r over the hypotenuse, over little r like that. Sine of theta, opposite, r over hypotenuse, little r like that. So you can fill a bunch of stuff in. And I'll just say that dBz is equal to mu naught over 4 pi I. We'll still have the dx and the r squared down here, and the sine theta will be capital R over r like that. So I'll let you sort of dig around in your book. I think I even have another video on this exact same derivation. I just want to cut to the chase now and say, if we work all this down, you know, a few steps in there, and we realize that BC is the integral of dBz and that sort of thing, and we keep going, we'll eventually get that the magnetic field due to the ring is something like this. It's going to be something like mu naught r squared over 2 times the quantity r squared plus x squared to the 3/2 power, and we get our result. So I'll just say that these derivations are kind of nice. They're kind of minimal for this particular section of the class. We don't have too many of these to go. This is a great laboratory quiz problem, a great midterm exam problem to see if you can really hash all these things out with all these weird angles and considerations of the cross product. And so I'll just wrap this video up with one last bit of a concluding remark about where we are now. We have a couple of nice systems, don't we? And I will continue the wrap up in the next video.